Hi everyone, in today's video we're going to go a little more in depth to these Riemann sums that we've been talking about, and then we're going to make connections between these sums and some other types of notation that you're going to see pretty commonly when it comes to the AP exam. So the first thing I want us to remember when we're talking about these Riemann sums, what we're talking about are those rectangular approximations that we've been using to estimate the value of an integral. Rectangular approximation. And again, we've been using those rectangular approximations to estimate integrals. And so hopefully you remember, right, we've had three. We've got LRAM, MRAM, and RRAM. So we've been using those rectangles and summing them up to estimate the value of an integral. So in some questions we're going to be asked to make a determination about the accuracy about those sums. So some Riemann sums provide overestimates of the actual value of the integral, and some provide underestimates. So sometimes we can determine whether our estimate is an over or underestimate using features of the function. Now, this is a big deal here. When asked, it is always best to draw a picture to answer this question. So in other words, I would not try to memorize what we're going to go through now. I would make sure you understand how to use a picture to be able to reason through this. So let's think about a right Riemann sum. Another way of thinking about this is our right rectangular approximation. Sorry for squeezing that in there. Right approximation, or what we call RRAM. So if I want to determine whether this approximation, this right Riemann sum, is an over or underestimate, I'm going to look at whether the function is increasing or decreasing. And that information is usually going to be given to us in the instructions. So let's take a look. Let's say I have an increasing function. I don't actually care what the actual function is doing. I'm just going to draw kind of a generic increasing function. Looks like that. And then I'm going to make myself some subintervals. Now, I know if I have a right Riemann sum, I'm using the right endpoint of each of those intervals to determine the height of my rectangle. So here I'm going to go up to the curve and then over to the y-axis to make my rectangle. Same thing here, up to the curve and over, up to the curve and over. And what we should notice here is then I have pieces of these rectangles that lie above the curve. Since I have pieces that lie above the curve, I know that this is an overestimate. So in this case, a right Riemann sum is an overestimate. And if we were asked to justify, we would say because our function is increasing. Now again, I'm not going to try to remember or memorize that every time I'm using RRAM, if it's increasing, it's over. I'm just going to draw a picture to help me reason through that. Now, if on the other hand, let's say our function was decreasing, so I've got something like this. I'm going to draw in some subintervals and I'm going to just reason through it. Now I'm going to use the left endpoint. So from 0 to 1, my left, or excuse me, I'm still using RRAM. So I'm still using my right endpoint. So from 0 to 1, I'm going to use 1, I'll draw it in green, go up to the curve and over. From 1 to 2, I use the right endpoint at 2, up to the curve and over. And then again here, up to the curve and over. So here you can see we've actually got gaps where we lie below the curve. So in this case, we would say that a right Riemann sum is an underestimate. because our function is decreasing. Okay, so that was for right Riemann sum. So now we're going to look at our left Riemann sum. Again, we're just talking about LRAM, our left rectangular approximation. Again, it's still looking at whether it's increasing or decreasing. And we're going to use that same kind of process of sketching a picture to figure out whether it's going to be an over or an underestimate. So let's draw our increasing function again. Here we go. And I'm going to draw in some subintervals. And now we're going to test our left Riemann sum for an increasing function. So now from 0 to 1, I'm going to use that left endpoint to determine the height. From 1 to 2, my left endpoint is 1, so I go up to the curve and over. And I do that for the same thing. And I can see all of those rectangles lie below my curve. So this area that I've accumulated here is less than the total area under that curve. So here we would say if it's increasing, this is an underestimate. Now, we would still technically say that this left Riemann sum is an underestimate because f of x is increasing, but for the sake of time here, I'm just going to make note that that's an underestimate. For decreasing, we can see why. We can probably anticipate now or guess, predict that this is going to be an overestimate, so let's go ahead and see. Drawing a decreasing function, and now we're using our left interval or a left endpoint. So I'm going over and over here and over. Oops, I'm a little off there, but we still get the idea. All these orange parts are above that curve. So now the area accumulated in those rectangles is more than the area under the curve, so this is an overestimate. So the key piece when I'm looking at a left or a right Riemann sum, the key feature I'm concerned about is whether that function is increasing or decreasing. Now when we look at our trapezoidal sum, we're instead going to look at whether the function is concave up or concave down. And again, they're usually going to give you this information in the problem setup. So let's take a look. If we are concave up, so I'm just going to draw a parabola here, let's say, and we'll do a couple subintervals. So now to construct my trapezoids, now I need both endpoints of the interval. So I'm going up to here for one base, up to here for one base, and it's not real clear to see, but if I connect those, I'm actually ending up above the curve. And I can see that happens kind of every time here. That's a little exaggerated there, sorry about that. And if I connect these, I end up above the curve. It's a little hard when I sketch, but I can see I've kind of overestimated this area. So in this case, if it's concave up, we would say the trapezoidal sum is an overestimate because the function is concave up. Now, if we look at concave down on the other hand, and again, apologize, my sketches are a little rough. It's a little hard to show this, but kind of do the best we can here. I'm just going to make a couple intervals. Now, if I'm doing my trapezoids, I've got from here to here, and I'm going to connect that, and from here to here. Hopefully we can see now when we're building out these trapezoids, that area, those trapezoids lie below the curve, so we would say this is an underestimate. Again, the big idea here is not to memorize this information, it's to be able to use this process of making a sketch and sketching in some either rectangles or trapezoids to be able to come up with that interpretation. So here's a question where we'll kind of practice with this. This is a typical FRQ covering this topic. So it says we may use a calculator. Water is being removed from a tank at a rate modeled by R of T, liters per hour, where R is differentiable, just means I can take a derivative, and it's decreasing. So based on what we've been talking about, I know this is important information. It's decreasing, and selected values are shown in the table below. So it says use a left Riemann sum, and we want 4 subintervals that are in the table to estimate the total of water removed from the tank. So we're going to set up our intervals. I've got 0 to 1, 1 to 3, 3 to 6, and 6 to 8. Those are my 4 subintervals, and I want a left sum, so I'm going to use that left endpoint. So at 0, I've got 1,340. At 1, 1,190. At 3, it's 950. And at 6, it's 740. So what we're actually doing is we're estimating the integral from 0 to 8 of R of t dt. Right? This function is the rate at which it is being removed. So the integral is going to give me the change in the amount there, how much was removed. So now I have to be careful. These intervals are not a common length, so I have to handle each one individually. So my first one, the base is 1. The height is 1,340. Plus, now I have a base of 2. We can mark that there. The length from 1 to 3 is 2. So 2 times 1190. Plus, this is going to be 3 times 950. Plus, what do we have? 2 times, 740. And let's see what that gives us. I'm going to use my calculator really quick. And I get 8,050. Now my units, since I multiplied hours times liters per hour, is going to be liters. So there is our estimate of the value of that integral. So now it asks us, is this an overestimate or an underestimate of the total amount of water? And it asks us to give a reason. So again, when they're asking over or underestimate, I know I have to think about whether the function's increasing or decreasing. In this case, it tells us it's decreasing. So all I'm going to do is just sketch some generic decreasing graph. Put in some subintervals and sketch. If I'm using a left Riemann sum, I know it's going to look something like this, and I can see those areas lie above the curve. So I would say that this is an overestimate So that's my answer. It's an overestimate. Now a reason, I would just say because my function R of t is decreasing on that interval which was from 0 to 8. So the reason is because R of t is decreasing. All right, let's go ahead and flip over. I'm going to skip number 2 because it's pretty much the exact same question, and if we have questions about how that works, we can talk about it in class. So we're going to move on to the next idea here, which is if we could add together an infinite number of rectangles, we should approach an exact answer. So if I could divide this up into smaller and smaller subintervals, my rectangles or trapezoids would get super close to the exact answer or the exact value of that integral. So we're going to connect up some notation that can be used to represent this idea. So here's how it looks. This is what we call summation notation. So this right here is what we use. It's called sigma, and it's used to represent a sum. So we're adding things up. Now, in our case, n is the number of subintervals. So it tells us basically how many rectangles we're using. So the idea is that I'm taking n approaches infinity. I'm getting infinitely many rectangles, and then I'm adding up all of their areas. Now in here, I have my function f of x, right? That's representing my y values, or the height of the rectangles. And then here, I have the change in x, so really that's kind of the length of my subinterval. Which serves as the base of my rectangle. With the idea being then, if I multiplied these two quantities, the height of the rectangle times the base, I should get the area of the rectangle. So this is kind of a complex way of saying, hey, let's let the number of rectangles approach infinity and then add up all of those areas. That should get real close to the actual value of the integral. And we represent that exact value using our integral notation. The integral from a to b, we get that from our interval of f of x. We still include our function, so the function carries over from summation notation, and this delta x in our integral notation becomes dx. So really the only thing we have to be able to do with that is to be able to translate from summation notation and rewrite it in integral notation. So here's how that works. I'm going to start off my integral always with the integral symbol. Now, the bounds of my integral are going to come from my interval. So -1 to 3. Now, here was my function, right? It comes right after that delta or sigma. So it's all of this. And the idea here is these things that look kind of strange to us, the m sub k, we're just going to translate those into x's in our integral notation. So the idea is that this just becomes 3x squared minus 3x plus 5. And then our delta x is just replaced with a dx. So they're not asking us to evaluate the limit, or the limit, or do anything with it, just express the limits as an integral. So the next one works very similarly. We have the integral. My bounds come from my interval. My function is here, the square root. And this c sub k is just my x. So what I have is the square root of 4 minus x squared. And then the delta x becomes my dx. So I have expressed that limit as an integral. All right. As always, we will address any questions that you have when we're back in class, and then you'll have a good chunk of time to practice with this. All right, make sure you took good detailed notes, and I will see you back in class. Thanks.